Expressing a number as a sum of two squares. First of all, let's look at a very simple case where we can see the answer straight away. So for 109, we can see by mere observation that it's 10 squared plus 3 squared. For 261, we can see by the digit sum that the number is divisible by 9, and so we can express it as 9 times 29. And then if we know that 29 is the sum of two squares, 5 squared plus 2 squared, by mere observation, we can simply multiply the 5 and the 2 by the 3 outside the bracket and get 15 squared plus 6 squared, using proportionately sutra. 867, as a sum of squares, the digit sum is 3. If we add these digits up, we get 21, which adds up to 3, and so we say it can't be done, it can't be expressed as a sum of two squares, because if the digit sum is 3 or 6, the number can't be expressed as a sum of squares. This is explained in my paper. Similarly, 558, we factorise it. We take out the factor of 2, then the factor of 9, and we can see that 2 and 9 can both be expressed as sums of squares, but the 31 can't be, and so 558 can't be done. Now here's a special method using the vertically and crosswise sutra. Take the number 74, factorise it. We get 2 times 37, and both of these numbers can be expressed by mere observation as the sum of two squares. That's 1 squared plus 1 squared for 2, and 6 squared plus 1 squared for 37. We combine these together using vertically and crosswise. So here's the 1, 1, and here's the 6, 1. And we multiply vertically and subtract. So 1 times 6 minus 1 times 1, we get 5. Then we multiply crosswise and add. So we get 1 times 6 plus 1 times 1, which is 7. So 74 is 5 squared plus 7 squared. Another example, 85, we factorise it. We recognise that we can express both of these as a sum of squares, 2 squared plus 1 squared and 4 squared plus 1 squared. And we do the same thing. We put the 2, 1 and the 4, 1, we multiply vertically and subtract, we get 7. We multiply crosswise and add, we get 6. So 85 is 7 squared plus 6 squared. Now there's another answer, and we can get that by just changing the signs here. The minus becomes a plus, and the plus here becomes a minus. We multiply vertically and add, which gives us 9, and we multiply crosswise and subtract when we get 2. And so 85 is 9 squared plus 2 squared. The reason why we only got one answer in this example is because these numbers are the same, and so we would get the same number whether these were as they are or the other way round. So that's two answers. So now we can go on to the general method, and this table shows sums of squares in a chart form. So for example, 109 is 10 squared plus 3 squared. We only need to consider the numbers above this line of symmetry, this red diagonal line, because the numbers below are a mirror image of the numbers above. And if we look at this blue line here, these indicate numbers on this blue diagonal which are the sum of consecutive squares. So 41, for example, is 5 squared plus 4 squared, where 5 and 4 are consecutive. And all the numbers on diagonals perpendicular to this blue diagonal are odd. So 61, 65, 73, they're all odd numbers. Now in chapter 31 of Tetriti's book, he gives this sequence of numbers. The chapter is on sum and difference of squares, and I'm going to call these numbers Tetriti numbers because they give the way of expressing a number as a sum of two squares. a general method. Now look at the yellow squares here. They're all numbers which are around 700, and they show a distribution of entries in this table that are around 700. And you can see they take a diagonal perpendicular to the blue diagonal first of all, then they curve upwards. And if you take the differences of each of these numbers from the bottom number there, 685, you'll see they are the THG numbers. So the difference here is 4. The difference between 697 and 685 is 12, and so on. In fact, you'll see that for any number on the blue diagonal, the differences from the first number are THG numbers. So for 365 we have 369, which is 4 more, and then 377, which is 12 more than 365, and so on. And we're going to use that fact to express a number as a sum of two squares. Let's take an example. We want to express 73 as a sum of squares. First of all, express it as a sum of consecutive squares, the nearest you can get. And that's 6 squared plus 5 squared, which comes to 61. And a way of getting that is to take the number 73, halve it, and take a square root. So half of 73 is about 37, and the square root of 37 is about 6. So we get 6 squared plus 5 squared, and because that comes to 61, we hope that the 73 will be on the diagonal perpendicular to this, to the blue diagonal that starts at 61. Well, you can see the 73 there. It's 2 along the diagonal, 2 jumps. And we can predict that because if we complete this equation, we know that this number here must be a 12 to make it true. And 12 is the second THG number, T2. That tells us that we need to increase the 6 by 2 to an 8 and reduce the 5 by 2 to a 3. And that's the answer. And we've used two sutras here by the deficiency because we use that 12 to get to the answer, and also by addition and subtraction where we go from the 6.5 to the 8.3 by adding and subtracting 2. Let's take another example. 137. Okay, we're going to halve it and take a square root. We get 8. So we can say that 137 is 8 squared plus 7 squared plus some deficiency, which we find to be 24. Because 24 is the third THG number, we add 3 to the 8 and subtract 3 from the 7, and we're done. Now it could happen that our number is not actually on the diagonal. As you've seen, you remember those yellow squares I showed, they start off going diagonally up to the right there, and then they curve round. So let's look at an example that illustrates that and how we handle it. 281. Okay, we halve it, 140, we take a square root, which is about 12. So we start off with 12 squared plus 11 squared. And in fact, to make this equation true, we need 16. Our 16 is not a THG number, and that tells us that it's not on the relevant diagonal. In fact, if this number is not a multiple of 4, then the number can't be expressed as a sum of squares. So where do we go? What's happened is that the number we're looking for is not on that diagonal. 12 squared plus 11 squared comes to 265, and our 281 is not there because of that curvature I mentioned before. So what we need to do is to jump to a diagonal which is above this one here, starting at 221. So that means that these numbers, the 12 and 11, are both reduced by 1 to 11 and 10. The new deficiency is found by simply adding the old deficiency to 4 times this number here. So 16 and 44 gives us 60. 60 is the fifth THG number, you can see here. And so we're going to add 5 to the 11 and subtract 5 from the 10 to get the answer. We may need to repeat this process. If the 60 had not been a THG number, we would have had to have gone further and repeat it, so the 60 will be added to 4 times the 10 and so on. It's also worth mentioning there's an easier method which involves using not the THG numbers but a quarter of them. And if you divide these numbers through by 4, you get the triangular numbers, as they're called, and using those it's actually easier because we end up adding the deficiency to the last number there. We don't have to do the multiplication by 4 and the numbers don't build up so much. Anyway, that's how it works, and it's explained more in my paper, which is available here. And you can see how to determine the number of steps required to get your answer, and how to recognize the THG and triangle numbers and where they are in the sequence, and how we could work alternatively with the red diagonal instead of the blue one. So just to sum up, we had mere observation at the beginning, so 109 is 10 squared plus 3 squared. Those should be obvious. We can use the digit sum to rule many numbers out, so 411 is ruled out because the digit sum is 6. We can factorise the number, so we may be able to do it like we did for the 261. We multiplied the 3 by the 5 and 2 there. Or the vertical and crosswise methods, so for 85 we wrote it as a product, both of which numbers can be expressed as a sum of squares, and then we used vertically and crosswise to get the answer. And there's the general method where we express as a sum of consecutive squares plus a deficiency, like this one, and get the answer. And finally, if we may have a combination of the general and special methods, say 146, which is clearly twice 73, so we know that 2 can be expressed as a sum of squares, and 73 we've done over here, so you do a little work on that, and then you apply this vertical and crosswise pattern to get the answer, 5 squared plus 11 squared. Thank you.